So I also join everybody else in thanking the organizers for this nice workshop. I have the unenviable task of keeping you all away from your lunch, so I will try to keep this short. And since I'm also hungry, so so I'll talk. So I apologize to those who are terribly into biology. I mean, I have nothing to do with biology. So this is some exact results about a model, a one-dimensional exclusion process, where I have been able to, because of the inherent niceness of the model, to be able to calculate the full current statistics. So this is the preprint, and it will appear in JPhysics. So as everybody who is interested in non-equilibrium physics knows, current fluctuations are extremely important in this business, and my point of view is that it would be useful to have exact results for certain class of models to sort of get some intuition. Not claiming that this will help solve anything fundamental, but it would be useful to have exactly solvable models. So the model that I'm going to discuss is based on earlier work with collaborators on a non-abelian version of the abelian sandpile model, which everybody, many people here know very well. So it's defined. I'm taking a special case of this general model, which is defined on directed trees. Here I'm just interested in a one-dimensional lattice of n sites, and each site is either occupied or empty, and the dynamics is totally asymmetric. And I'll take the model to be disordered in this site disordered. So transition rates will depend on the site j, and I'll denote the rates by alpha j. So the model is as follows. So suppose you are at site j. Suppose there's a particle at site j. It tries to hop with rate alpha j to its right, but let's say that site is also occupied. Then it goes to the next site and so on, and until it finds the first empty site, and it goes and occupies that. So you can think about it in two ways. You can think of this guy at the jth site of jumping over everybody else, or you can think that instantaneously there are many of these small transitions which result in a net effect of a configuration like this. So this happens with rate alpha j at site j. On the other hand, this is a finite model. I mean, this is a finite system. So what if everybody is occupied to its right? Then this guy just hops, and just jumps out from the right. So both of these can happen depending on where the first non-empty site is located, if at all. Similarly, you can have entry from the left. There's a reservoir to the left which contains some particles. So a particle tries to enter from the left with rate alpha 0, but the first site is occupied, let's say. Then it tries to go to the next site and so on. So it will find the first first empty site on the left, from the left towards the right, and it will go and sit there. Okay, so that's the idea. Now what happens if everybody is occupied and the particle tries to jump? Well, it'll just jump, and it'll just leave from the right. So overall, there is no effect, but this is important to keep track of the current. So there is a particle transport. So in terms of the current of the model, this is, so is the, I hope the model is clear. Let me know if there are any questions. Yes, so alpha j's are disordered. So they're site disordered. So if a particle is at the jth site, it jumps with rate alpha j, no matter where it ends up. Okay, so I need, those of you who are familiar with this kind of thing know that particle is entering with rate alpha 0 no matter what. So it's a Poissonian kind of statistic. So the current is alpha 0. So no matter what configuration there is, particle is going to enter from the left with rate alpha 0. So the current in the system is alpha 0. But there's actually some other things that are true for this. So this is from old work. The steady state, even though this is a non-equilibrium process, it's totally asymmetric. The steady state is a product measure with the density at site j given by rho j, which is alpha 0 by alpha 0 plus alpha. Moreover, the Markov matrix, which is this 2 to the n by 2 to the n matrix, has extremely nice eigenvalues. So its characteristic polynomial, this p factor comes from the fact that there's a 0 eigenvalue with multiplicity 1. But there's also, all the other eigenvalues are in fact linear in the alpha j's. So for each subset of the set 1 through n, you have an eigenvalue which is minus alpha 0 minus alpha that subset. Alpha, where alpha s is the sum over all I in S of alpha I. Okay, so for each subset you have an eigenvalue. So current is well, it's the probability, for example, what's the probability that a particle crosses the 0th bond, the bond on the left I mean, there are several ways of saying this. What's the probability that a particle will enter from the left and cross this bond? Okay, well, since it's always going to cross no matter what the configuration is, so this is the current result. This, just by conservation of probability, this is the same no matter which bond you look at. Okay, so this fact about the eigenvalues is extremely nice, but there's no easy proof. Even though the result is so simple, there's no easy proof of this. At least I do not know. And as I said, the particle current is. Okay, so just to give you an example, this is the system of size 2, and the eigenvalues are here. Okay. So now I'm interested in the current statistics. So for each bond, I place a marker, I calculate the total integrated current. So Q sub T super I is the integrated current across bond I, which is this between site I minus 1 and I. And I keep, if you're an experimentalist, you keep something there and you track how many, you keep a detector there and you track how many are going in time t and you divide it by t. And so I'm interested in the joint statistics. So I'm interested in what is QT1, QT2, etc. All of them simultaneously. So suppose, and this is a non-equilibrium quantity. I'm not calculating this in the steady state, right? So I'm looking at it starting from any initial configuration. So what's the joint distribution of these guys being J0, J1, and so on up to Jn? Well, because the chain is ergodic from some general nonsense, mathematical nonsense, you can argue that in fact all of these have to be correlated. They have to be all the same in the long time limit, and they depend on a single. There's a single function that's going to come over here, which is known as the large deviation function. And the question is, what is this for this model? And experts already know the answer to that, but let me tell you what the technique is. I mean, how do you answer such a question mathematically? So what you do is for each bond bi, you have a parameter, let's say lambda I, and you form what's called the tilted generator, which I'll give you an example in a second. So for every transition which contributes to a particle going across bi, you multiply by e to the lambda I. And if since I have jumps which span multiple bonds, I have to sum over these guys or take the product over. So then this again a theorem that the largest eigenvalue of this tilted generator is the cumulant generating function is the joint cumulant generating function of the currents, and the large deviation function is nothing but the Legendre transform. Okay, so this is just some mathematical nonsense. You can take that as fact, a black box, and you just apply it. I mean, this is true for many classes of processes, and in particular it's true. So in our case, the tilted generator is this. So for example, for system of size 2, for example, there's a transition with rate alpha 0 where a particle enters from the left in configuration 1, 0. It hops over the first site and reaches to configuration 1, 1. This involves both the left bond B0 and the middle bond B1. And so when I construct the tilted generator, I multiply it by e to the lambda 0 plus 1. So the result that turns out to be true is that the joint cumulant generating function is given by this explicit formula, alpha 0 times the exponential of the sum of the lambdas minus 1. And the fact that it only depends on the sum of lambdas is related to the fact that the currents are all correlated. The large deviation function has this extremely simple. Okay, so this is the first result. But there's something nicer that happens, which is that I can say something about what is called the quasi-stationary distribution. So suppose you're looking at the system and you measure some atypical currents J0, J1, and so on up to Jn. Okay, so at some time you do this experiment, you wait, before it has reached stationarity, you mark these guys and you calculate these integrated currents, and there are some numbers J0, J1 up to Jn over some time frame. And you can specify this numerically by looking at the conjugate variables, these lambda i's. Now the fact that the currents are correlated forces each of these ji's actually to be equal, and in particular they'll be equal to this guy, alpha 0 prime, which is alpha 0 times exponential of the sum of the lambdas. And now you can ask the question as to what happens when you condition the system to have this atypical current. Right? So since it's a stochastic system, there can be atypical fluctuations, and if over a long time frame, so something like that could happen, but I'm looking at a time frame large enough so that those will be more or less equal. So maybe 102, 101 are okay, but 102 and 51 are not okay. I mean, they just won't happen. So now, conditioned on observing this atypical current, how does the system look like? So there's recently a technology that has been invented by Raphael Chatrit and Hugo Touchet called the generalized Doob transform. And what you do is and this is based on old work of Doob, you can create a new Markov matrix, which is like studying the steady state of the system. I mean, this is like studying the evolution conditioned on this atypical current. So this is a very generic formulation. You have this tilted generator. Ln's are the left Perron eigenvectors. Ln is the left Perron eigenvector for this matrix. You multiply it, you do this business. This is guaranteed to be a new Markov matrix. And this sort of determines the evolution of the system conditioned on this fluctuation. And the steady state of this guy is the quasi-stationary distribution of the original system. So this is just, again, this is just some technology. And the main result for this system is that actually the conditioned Markov process for this exclusion process that I'm studying actually is nothing but a renormalized version of the original process, with the only change being alpha 0 being replaced by alpha 0 prime. All the other alpha i's remain the same, exactly the same. And the only thing that changes is that the entry current changes to this fellow. Okay, so this is the sort of the main result, and I'm almost done. So as a corollary, the quasi-stationary distribution is also a product measure, has these densities, and this is the Markov matrix, and LNs have some algebraic properties, which I skip in the interest of time. There's a nice explicit formula for the eigenvectors and eigenvalues. And so I thank you for your attention, and maybe we can go for this. Thank you.
Is there any questions?
Yes, over there.
Arvind, can you go back to that generalized Doob transform?
Sure.
Yeah, what's the motivation? This is basically making the conditioning thing more probable. That's like,
so, I mean,
something like that.
No, so I think this line maybe explains it. I mean, suppose you observe, currents are long time observations. So
right.
You measure how many, so over this time frame, suppose you have this current, atypical current, then how do you characterize the evolution of the system conditioned on having this atypical current? That's given by this, this marker. You know, this is the same thing that you study for
Some tilting, essentially some kind of tilting.
Sorry?
Some kind of tilting. Right?
Yes, that's why it's called a tilt. This ln is a tilted generator. So it's exactly, yeah.
Can you solve the problem in a closed ring?
No, actually, no. So on a closed ring, the system, I mean, the system is not as nice. I don't think it's a product measure and the eigenvalues.
The other question was, is this model identical to the low noise limit of the Toom interface model?
No, because in the Toom interface model, you have bonds. I mean, you have domains. So you have ones followed by zeros, and then the rate that this guy hops. I mean, in the Toom model, you can have, so the rate that a guy hops from here depends on the size of the domain, I think.
Not in the version that I know, but.
But anyway, that's on the infinite line, and at least one side is infinite in the case. Yeah.
Any other questions? If there are no more questions, so let us thank the speaker again and let us end the session.